e k to the t, when it's saying like at a rate, do you just know to use the equation that is given?
Well, if this is at a rate, that means it's some derivatives, like it's like y prime or p prime.
Okay, so
It's
we
always
know
going to end up.
that's gonna be dy over dx or dt.
Yeah,
Okay.
dy over dt. But you're skipping the calculus process because you're just jumping directly to y equals c to the kt.
Okay, yeah, so like I'm looking at page number 1 of the test review. So like when it's like the amount of oil remaining,
Mm-hmm.
like that's, that it's talking about.
Let me look at the wording here. Yes, it's writing equation for y, and y just represents the amount of oil, right? So you know that, y prime equals ky is ultimately going to lead to y is equal to c if we separate our variables and do all that stuff.
And then for B, you just know that.
Yeah, we're gonna skip B. It's just A and C, creating all your order pairs and finding your C and finding your K.
Okay.
Yeah, you can. It's underneath. You can take the blue one below. Underneath.
Wait, Mr. Ian, can you go over problems like number 4 on page 14? It's like how to match the equation for the graph.
Yeah.
Because I kind of just didn't like connect it fully in my head. Like,
Hey, morning.
Wait, what page is this?
This is page 14. I'm going to do this one real quick before we start at number 1. So this is the process. Yeah, so I'll come back to this one a little bit later, but just want to kind of go through a little quick. You see how all these order pairs are positive slopes?
yeah.
These are positive slopes. So quadrant 1 should give us positive slope.
Mhm.
So quadrant 1 order pair could be like 1, 1, 2, 2.
Okay.
So some of these are not going to match very well because if you look at this first one, what happens if I plug in 1, 1?
So you do like.
And I don't see a negative here.
Yeah.
So this one can't be it.
Okay.
And if you look at, what about quadrant 3 or quadrant 2? What do you see quadrant 2?
Negative.
Negative. Quadrant 3.
Oh.
Quadrant 4. And some of these are not going to match it very well. If you look at x squared over y squared, what is this always going to give you? So these negatives shouldn't appear, right? So
Yeah.
this one's not right. Y squared over x, right? If I plug in -1, -1, okay, so that one gives me a negative slope. That's fine. Oh, x over y cubed. So this one here, if I plug in -1, -1, I will get a -1. I'll get positive. And this is not positive.
Yeah.
So this one's bad. So I'm just down to gonna be just in here.
Okay.
This is just you.
And if you look at your Y values, as your Y values are getting higher, like 5, 6, 7, 8, what's happening to my slope?
There's, slope there.
Well, not slope 0, but slope like maybe like very flat. Right?
Yeah,
So, so therefore, like, let's say if I plug in 5 or 1, 5. If I plug 1, 5 here, I'll get 5 squared over 1. This is a slope of 25. And I don't see a slope of 25 here.
yeah.
So,
Okay.
so then, so sometimes you have to kind of just look at some order pairs. And if you're down to 2, you're just picking order pairs. I know sometimes you don't know what this, what that slope is, but it's probably like a 0.1 or 0.2. It's fairly a positive slope.
Yeah.
Right.
Okay.
So you don't know the exact slope, but you have enough of an idea to kind of estimate these slopes and match it up with what you see.
Yeah.
All right, so I'm starting back with page 1, number 1. And then I have some additional practice worksheets there if we have time, but you can also grab those.
Really steep, yeah.
Okay, page 13. So we're going to start off by just filling in the slope field. So I'm going to just identify the location of each order pair. And I'm going to plug -1, 2 into my derivative equation. So -1 in for x and 2 in for y. So -1 minus 3 is -4. And then 4 minus 1 is 3. So -4 times 3 is -12. So that's a really steep slope. So you just have to indicate that with a steep slope.
Do we have to show that how steep it is, or can we just make sure it's like negative and positive?
Yeah, pretty much negative and positive. Yeah.
Okay.
Or just try your best to estimate that slope, but it's not really that big of a deal. So I'm just going to go down the line here. So -1, 1. If I plug -1 in for x, 1 in for y, I get again -3 times 1, so -3. So not as steep, but still negative. And -1, 0 will give me positive. Okay. You don't have to write out all these order pairs. I'm just making it clear that what we're plugging in to get to interpret. So a bunch of these are just positive and negative slopes. But let me just kind of give you an instance, some things that you're not seeing here. What if it was like dy dx is equal to x minus 1 over y at 1, 2? What would this give me?
That give you 0 on the top.
Right, and the bottom will be 2. So 0 over 2, what would that look like? That's 0. So that's just a horizontal line, right? Okay. What if it was again dy dx x minus 1 over y, and the order pair was 2, 0? It'll be 1 over 0. Then what would you do at that order pair?
Leave it.
Leave it blank. Yeah, leave it blank. If something is undefined, you leave it blank. If it's 0, you do a horizontal line. Positive slope, you know what that looks like. Negative slope, you know what that looks like. So there's 4 options, right? 4 options of what you can do through an order pair. All right. Any questions with part A? Again, I have additional handouts there. There's just some additional practice problems in case we get through this. And then also additional formula sheets if you want to practice through those formulas before the test. All right, part B, find the particular solution. So we know we have to solve this differential equation. We have to go through our full process. All right, separate our variables, take the antiderivative, solve for C, solve for Y. All right, cross multiply. Okay, so we have our dy and dx's in the right places. We're not going to move these anymore, but do we have full separation of variables? Right, what's out of place? Yeah, so 2y minus 1 has come to the left side. Divide that over to the left side. And now I can drop the parentheses because now I have full separation of variables. So I wanted to hold on to those parentheses until I have separation of variables. And also with parentheses, we never want to expand out, right? They're trying to help us. The problem is trying to help you separate and keep things where they belong. Okay, so right side is just power rule, but left side is a little bit more complicated. We got to go through U substitution to clean up that left side. So our U value is the denominator.
Wait, why couldn't you do just like L in and then put the 2y minus 1 in there?
I mean, for the most part, it's going to be that, but the 2y minus 1 will produce a derivative, and we need U substitution to keep track of that coefficient. Now, if it was just y minus 1, then we can probably jump to that process because there's no derivative except 1. But yeah, that 2y minus 1 is going to leave us with a little bit more than, sorry, du over 2. Okay, cross multiply. All right, so all this work is just trying to get this left side cleaned up. So I have 1 over u times du over 2, right? If we didn't do U substitution, we would have a harder time, I think, to understand, oh, there's a 1/2 that we got to keep track of. But the shortcut is that because the derivative of 2y minus 1 is 2, it's always going to produce the reciprocal of that. So if you're comfortable with those connections, you can do that. But otherwise, go through U substitution so you know exactly what's going to come out of that derivative. Okay, so 1 over u du, that's just going to be natural log of u, and then replace the u back in terms of y. Okay, so a lot of work on the left side, and the right side is just power rule. So equals x cubed becomes x to the 4th over 4. 3 becomes 3x, and then plus c. So if you can get to this point, I'll give you majority of the points because you've done the most important part of the work, which is separating the variables and finding the antiderivative. You've done all the calculus. It's still important to solve for y and solve for c, but those points will be less. All right, same thing on the AP exam. They're going to prioritize the calculus over the algebra. Any questions up to this point? So two things left to do to solve for y, solve for c. It doesn't matter which order you do them in, but if I see the equation being difficult to plug in and solve for c, I typically wait. So I want to solve for y first because I just want to get to that point before I solve for c. Now, I would like to raise both sides with e as the base, but that 1/2 is kind of getting in the way. I'm not quite able to get that clean relationship if it's 1/2 e to the 1/2 ln. Either I can bring that 1/2 up as an exponent, but I think the easier thing to do is I can just divide both sides by 1/2 or multiply everything through by 2. Force, I'm just trying to clean up that left side. And as I clean up, I can also move towards solving for y there. So I'll distribute the 2 through. 2 divided by 4 or 2 times 1/4 is going to be 1/2. 3 times 2, 6x. And then 2 times c, I know that's just a constant, so I'll still leave it as a c. So now this natural log is a lot cleaner for me to match with the exponential base e. Now base e comes in. E and natural log goes away. That's what our whole purpose of doing that. And I'm going to separate that c away from my variable expression. So e to the 1/2 x to the 4th minus 6x. Remember, this plus is going to turn into something else, right? It's going to turn into what? Times e to the c, right? Multiplication. Make sure that you're understanding that it's no longer plus c. The exponent addition is going to turn into a base level multiplication. And we know e to the c is just one giant c. Pull that c out in front, drop the absolute value. Good so far. So I'm going to go ahead and move towards solving for y. So I'm going to add 1 to both sides, divide by 2. All right, divide by 2. So if I divide by 2, I'm dividing by 2 for both these terms, right? What's c divided by 2 going to be? Still c. So y is equal to c e to the 1/2 x to the 4th minus 6x plus 1/2. There's my general equation.
Could you just do the -2 or the dividing the 2 under the whole equation? Like, why are you separating them?
It'll just make it easier for me to solve for c without having to deal with that fraction. I find it easier because we still have to solve for c, right? If we solve for c, it's not wrong if you divide everything by 2. I just find it easier to split up. Okay, one last thing to do, and that is to solve for c. So the order pair is 0, 1, 0 in for x, 1 in for y. Now, the nice thing about the 0 is it's going to wipe out my exponent, which will make things easier for me to evaluate. 0 minus 0 is 0. E to the 0 is not 0, right? E to the 0 is 1, but it still helps me out. E to the 0 can go away. That's just 1. So if I do 1 minus 1/2, I get 1/2. So c equals 1/2. And then bring that 1/2 back into your general equation.
So if you multiply, divide anything by C, then C just absorbs it.
C will take in everything, yeah. It'll take in plus or minus, it'll, yeah, take in multiplication of coefficients. I mean, you could keep track of that divided by 2, but you don't have to. I mean, it's just add an extra step into your problem if you did that. All right, are we good with part B?
Get in. Like I looked back at the info and like I see it makes it easier, but that wasn't my first.
Oh, you mean the 2y minus 1? Well, that's fine, but there is a coefficient that of 1/2. Were you able to catch that 1/2 on your own?
Yeah, afterwards. But I'm just confused on why I did it originally because I just went straight to the natural log of.
Right. Well, the bit of a shortcut is that if you know that this 2y minus 1 will produce a 1/2 coefficient, you can basically skip all this u substitution if you understand that there's a 1/2 left over. But I still have students do this because that's just another thing you have to memorize if you understand that concept. So that u substitution is just to help keep track of what coefficient is going to be left over if you're not clear what's going to show up. But yeah, I mean, if you jump from here to here and you understand that there's a 1/2 there, I won't take off any points if it didn't show this work, if that's what you're asking. All right, part C, this is a different process, right? Equation of tangent line is not, it should be a lot easier. And you're just gathering your order pair, gathering your slope, point slope form. It's just first semester topic. It's barely any calculus. You're just, I mean, it's basically algebra. All right, so equation of tangent line at x equals 0. So that's the same point that is given here. So we'll use that same point. And I need slope. How do I find slope? Use what? dy over dx. My dy dx is my slope formula, right? My derivative gets me slope value, just like how I did so with my slope field. So take my order pair, 0, 1, and plug it into your dy dx. -3 times 1 is -3. So we have our order pair and our slope. Now put into point slope form. Y minus 1 is equal to m times x minus x of 1, so x minus 0. Okay, so this is my tangent line equation. Okay, next up, linear approximation. So this is where I'm going to plug 0.2 in for x and get y by itself. So y is equal to -3 times 0.2 minus 0 plus 1. You can leave it like this, or you can give me a decimal value with your calculator. All right, number 2. This looks like a u substitution problem. If I get my denominator rewritten, I should be able to identify that u value. If we're doing u substitution, we typically want to target our portion inside the parentheses.
So for this one, are you not using like the arc sine or tangent?
Yeah,
just because you know that it doesn't fit, like the equation doesn't fit with that.
Right, right. And also, there's no easy gap for me to identify, right? It's not like x to the fourth versus x squared. There's no gap of two or more.
Okay.
If you look at this u value should handle this derivative pretty nicely. So that should fit pretty well. Okay, du dx. Again, you know you're on the right track if you can think about the derivative and see a version of the derivative elsewhere in the problem, right? If you see that pair, you know, you should be able to see, you know, whether things are going well, having that indication there. So this is a good sign, right? That 2e to the x, because we do need these to eventually cancel out, and they will. Okay, so replace my underlined portion with u and du.
I have a question for the du over dx. If it was like 2e to the 2x, would you multiply the equation by 2?
Yeah, it'll be 2e to the 2x times 2, because e to the u's derivative will be e to the u times u prime. All right, e to the x cancels out. I can pull a 3/2 out in front. All right, what rule do we use for this problem? Power rule. Okay. I know it's tempting to do natural log because you see that u in the denominator, but it's not natural log unless it's u to the first power. Anything else, you got to bring it up and make it go through the power rule. Okay, so there's my power rule. U to the negative 1/2 becomes u to the 1/2 over 1/2. I'm ready to think about evaluation. I would like to flip that 1/2 up as 2. So 3/2 times 2 is just 3. And 3u to the 1/2. Again, we got to be careful that this u is not quite compatible with the 0 and 3. Let's bring back our original variable x. Now that your x's are back, you can think about the 3 and 0.
Wait, I'm confused. I thought for power rule you're supposed to do add 1.
Mm-hmm. So what's negative 1/2 plus 1?
Oh, it's negative.
Yeah. If it's positive 1/2, then it'll become 3/2. But we have to adjust that 1/2 below to make it negative 1/2 above, because we only can do power rule when that u is sitting up in the numerator to begin with. Okay, plug in upper and lower bound. And then once you plug in, you don't have to clean up. So plug in the 3. You can leave it like this. I went one step further and I made 1 plus 2, 3, but either is fine.
Because I did, but I don't know if that's.
Well, same. I'm going to have the same conditions as AP exam. You can leave your answer unsimplified as long as they're all numeric values and you plugged it in right. You can leave your answer unsimplified. Yeah. The only exception, which is not on this test, the only exception is if there's trig. If there's like tangent of pi over 3, you got to go one step further and get a ratio. But if they're all numeric values, leave it. Yeah. All right, 14. Page 14. The rise in population of a town is directly proportional to the number present. So rise in population, that's a rate, so that's P prime, is directly proportional to the population. So it's always going to end up being these equations. And you know that your differential equation is that P prime equals KP. and your general solution is always going to end up. So we're skipping the calculus because we know where it leads. So there's my differential equation. Here's my general solution. All right, so we know we're just working with this equation and we're just building a bunch of order pairs here. I like to start off with understanding what my X and Y values are. T for time, P for population. Population doubled in 50 years between 1920 and 1970. In 1998, the population was 75,500. What's the population in 1920? So I like to pick out the earliest time and call it T equals 0. So in 1920, we know there's some starting population. We don't know what it is, and that's what we're looking for. Can we create an order pair from that first sentence? Population doubled in 50 years between 1920 and 1970.
50.
Yeah, 50 years later, my C is going to double. My unknown initial population is going to double. In 1998, population was 75,500. How many years after 1920 is that? 78. So 78 years later, my population is going to be at 75,500.
How do you, like, are you just assuming for 0, C that in the beginning there's a 0 population?
Oh, no, 0 is for 1920. 0 is for time, right? So in year 0, there's an unknown population that we don't know yet.
So I'm confused. How do you know that the time was 0?
So anytime we are working with these problems, we always want to work 0 into our problem. So whatever the earliest time in the problem is, that's going to be your year 0. You don't have to do that. It just makes things a lot easier, I think, when you can involve 0. It's just you have smaller numbers, and also sometimes 0 can help you cancel stuff out. Okay, so we know that normally we would plug this in and find C, but we don't know what C is. So we're going to skip this and move to the second order pair. All right, so I'm going to plug this into my equation and see what that gets me. What can I plug 50 in for? T, right? 50 is my T. 2C will plug in for E. Yeah, so. All right, what can I get rid of to make things easier? C, divide both sides by C. So I know I'm trying to solve for C, but we kind of have to find something else before we can solve for C. So we're kind of have to focus on what the equation can get us. I want to solve for K, but K is stuck in the exponent. So do what? Natural log. Because we know natural log has a nice property that allows the exponent to freely move without changing the overall value. 50K can come down. Right? What do you know about natural log of E? Becomes what? 1, right? Goes away. Solve for K by dividing by 50, right? So no decimal value for K. I want you to hold on to that K value. So let's go back to our general equation and update with the information that we found. So maybe now we can involve the last order pair. Maybe this can help us solve, right? So 78 plug in for what? 75,500 plug in for E. So if I replace these with numbers, the only variable, the only unknown that we have left is C. So we should be able to algebraically just go through our process and solve for C, right? Now, e to the natural log of 2 or 50 times 78, that's just going to be one messy number. So I can just take that, divide it over, and that should give us our C value. All right, so practice putting that in your calculator. See if you're able to get what I got here. Right, everybody okay?
We need to say the units on the test, or can we just leave it like that?
Yeah, I can just leave it like that. Oh, and then as a side note, on the AP exam, you would not get taken any points off for units if they don't ask for it. So they can only take off points if they ask for something. So yeah, keep that in mind. All right, number 4, match the differential equation with the slope field to the right. So I like to look for 4 things in my, just to kind of gather information so that I don't have to plug in a bunch of information. So I like to look for positive slopes. I like to look for negative slopes. Where do I see a gathering of negative slopes? I like to look for slope zeros. And I like to look for slope undefined. Slope undefined will be, you see a gap, right, where something has nothing on it, whether it's a line or a series of values. So I like to look for 4 things, and whatever stands out in terms of, oh, this quadrant is all this slope, or oh, there's a vertical line where there's nothing on it, or there's everything on one side is positive slope, slope 0. So for positive slopes, I see quadrants giving me nice collection of similar slopes. So quadrant 1 is positive. Where else do I see positive slopes?
Screen's full.
Oh, sorry. So again, I like to look for 4 things here: positive slopes, negative slopes, slope 0, slope undefined. It doesn't mean that I'm always going to have those properties show up on every slope field, but those are the easy things to spot, right? I mean, it's hard to look at a slope and say, okay, that's definitely a slope negative 12, right? We don't know that. We may know a steep slope from a gradual slope, but these should be easy to spot. Okay, so a positive slope, quadrant 1. Where else do you see positive slopes? Quadrant 4. So that means any ordered pair from quadrant 1 and quadrant 4 should return me a positive number. Where do you see negative slopes? Quadrant 2, quadrant 3. Slope 0, I would say that y-axis there when x equals 0. And slope undefined it may be at y equals 0, but just have to be careful with the x-axis. Sometimes it could be hiding a slope 0. So slope undefined could be maybe y equals 0, but we just have to be aware that, that this is no guarantee because it's one or the other. So we would like to eliminate some choices that are obviously conflicting with what we see in front of us. Is the first answer choice going to give me a positive slope in quadrant 1? What happens if I were to plug in order pair 1, 1? I'll get a negative, right? I don't see any negative here, so this one can't be it. The second one looks like quadrant 1, quadrant 4, quadrant 2, and 3. Looks like these could still stand. So we'll come back to B. What about C here? X squared over y squared will always give me what? Always positive. But if this is always positive, it's not matching up with what I see here, right? I see some negatives here that's conflicting with that, so I can remove that. X over y cubed is positive in the first quadrant. But what if I plugged in a fourth quadrant order pair, like 1, negative 2? One over negative 2 cubed is negative, and negative doesn't match with what I see here, so this one is out. Okay, so I'm down to 2 options here, either B or E. If I look at E here, though, well, one thing is that so once you're here, maybe you have to kind of look at some individual order pairs and see maybe something in the first quadrant can kind of tip us off in terms of which one is going to be a better fit. If you look at your y values, what's happening as my y value gets higher? Right, what's happening to my slope? Right, it's flattening out. Right, my slope is flattening out. So let's say a y value of, of 5 or 6. Let's say an order pair of like, 2, 5. Right, order pair of 2, 5 should be something that is relatively small. But if I were to plug 2, 5 in here, I will get 5 squared over 2, which will be 25 over 2, which is like slope 13. And slope 13 should look a lot steeper than that. Meanwhile, over here, if I do 2 over 5 squared, 2 over 25, that's barely positive. And that looks like barely positive to me. So once you're down to 2 choices, you may have to look at some individual order pairs and see, okay, this order pair looks like it's 1/2, and see if that is matching up or get it or close to what you're expecting from your slope. Obviously, you're not going to know the exact slope, but something like 13 versus 1/2 or 13 versus 2 over 25, that should be easy to see the difference on the slope field. All right, number 5. What's our strategy here? Are these independent of each other? Yes, that's a good sign. That means we don't have to, it's like solving 2 problems. We don't have to find a U value that connects with the other. We don't have to merge anything together. These are 2 completely separate problems, each with their own U value and each with their own integral rule, right? Sine's antiderivative is negative cosine. Cosecant antiderivative is one of the newer ones that we learned, negative natural log cosecant U plus cotangent U. So we just go through our process, go through U substitution, find our derivative, keep track of our coefficients, and go through that process. So let me walk through those steps. So on the sine side, you don't have to do this. I just wrote it out with two integrals, so it's just visually reminding me, okay, these are two completely separate problems. They're not going to impact each other at all. I'm going to solve them independently, and in the end, I'll just put them next to each other. And each with their own independent u value. So this u value is pi over 3x. Derivative is pi over 3, cross multiply, solve for dx, I get 3 over pi. And so if I replace my u with x, sorry, my x with u, I have sine of u times 3 du over pi. There's a coefficient of 3 over pi. And I know that I have to include this as part of my antiderivative. Okay, we'll come back to that. Here, cosecant u value is 5x. Derivative is 5, cross multiply, dx equals du over 5. This reminds us there's a 1/5 in front. So the 5x will produce a 1/5. The pi over 3x will produce the 3 over pi. So if you understand that it's just the reciprocal of the derivative, you can skip that step if you're comfortable. If not, then go through the u substitution process. It's up to you. Right, so now sine's antiderivative is negative cosine. We can bring back the x after we find the antiderivative. Cosecant antiderivative is negative natural log cosecant u plus cotangent u. There are two negatives here, one from between the two terms and one from the integral rule itself. So two negatives becomes positive, and then replace the cosecant u with 5x, and then just put them next to each other.
Wait, where did the negative 1/5? Oh, is it just a part of that equation?
That one, oh, where the negative came from?
Yeah.
Yeah, so the negative came from the cosecant. Cosecant has its own negative. It's negative natural log cosecant u plus cotangent u. So this negative is from the problem, and then this is from the rule.
Okay.
All right, page 15. So from the very beginning, we should be able to spot this and tell this is probably going to be one of our trig rules, because you see how there's a degree 4 and degree 1. That's a large enough gap where we can't just use u substitution and expect the variables to pair up. So we know this is going to be one of our trig rules. Going to end up being the arcsecant, because you have inside the square root, you have the variable being positive and the constant being the negative. So this is the rule that we're kind of working towards.
What if they add, like, what if that was +7?
I wouldn't be able to give you that, because there wouldn't be a rule that would fit that.
I was thinking it'll always just work.
Right. Yeah, it has to fit into the rule. Yeah. There are some problems that we're not able to solve, and the ones I give you, there will be a definite rule that you can match up with. So from this point, we know that, okay, the nice thing is there's no need for completing the square. Everything is kind of ready for us to kind of get our parentheses ready with our u value. So we know that we can put inside the square roots parentheses squared minus parentheses squared. Right. So what can I put inside this set of parentheses so that if I square it, I get 16x to the 4th? Or x squared, right? 4x squared will fit nicely because that will be the same thing as this. And then for the 7, I can put what inside and square it and get 7 for the 7. So once you can identify those values inside the parentheses, then you're staring at your appropriate a value and u value. And again, the way you tell the difference between the A and U value is, does it have a variable in it? If it has a variable in it, that's going to be your U value. If it's just a constant, that's going to be your A value. Okay, so my A value is root 7. My U value is 4x squared. I got to go through U substitution still because that 4x squared is going to produce something. And also, I need to take care of this x, right? This x in the numerator needs to be paired up and canceled out. So derivative is d over dx is 8x, dx is du over 8x. I'm going to start replacing all my parts with a's and u's and see what I have left. It should match up nicely with the rule that I have in front of me. X's cancel out. That's good. We do have a keep track of a 3/8. All right, so I need to go through my rule for 1 over a, but I need that 3/8. This 3/8 is outside of my rule, so but it's a coefficient, so I need that. So 3/8 times 1 over a. My a value is root 7. Arcsecant, absolute value of u over root 7 plus c. All right, can you tell what process we need to do with 7? Okay, now how do we know that this is arc trig as well? How do you know it's not a normal U substitution where you set the U value equal to the denominator? Degrees, yeah, degree 2 versus degree 0. That's a large enough gap where it's not a normal U substitution problem. But the denominator is not quite set up, that trinomial. We have to go through completely the square so we can kind of get that binomial square to show up. So let's work on that. Right, what formula do we use to fill in the space?
B.
B over 2 squared, yeah. My B is the coefficient of my second term. So 16 over 2. 8 squared is 64. Okay, this should factor nicely. Multiplies be 64, adds to be 16. Should be the same numbers, right? 8 and 8. And this ends up being just plus 3. All right, let's get it all set up with our parentheses showing. X plus 8 squared. So that should fill in nicely. And what about my constant here? Root 3. A is the constant, U is the variable. This one will not produce a coefficient other than 1, so it won't be an additional thing to keep track of there. I'll pull the 7 out in front. My arctangent rule is 1 over a arctangent u over a plus c. So the 7 comes first, since that's outside of my rule, outside of my term here, times 1 over a arctangent of u over a plus c. Okay, number 8, can you look at this problem and recognize what type of problem this is? Synthetic division, right? There's a certain look to synthetic division. It's always like divided by x plus 1 or x minus 3 or x plus 5, right? It's always just 2 terms and it's just a linear term. And usually the numerator is a higher degree with multiple terms. So, okay, so we start off picking out the opposite term, opposite solution, x value. So -1 goes out outside your half box. 2 for x cubed, then what? 0 for x squared, then 0 for x, and then -5 for the constant. Okay. Are we good there? All right, first step, always drop the first number below the line. If it's a 2, drop down to 2. If it's a 5, drop down to 5. If it's 7, drop down to 7. Okay, once the number is below the line, then multiply with the factor outside. 2 times -1 is -2. Inside the box, you add. 0 minus 2 is -2. Multiply. -2 times -1 is 2. Add. 0 plus 2 is 2. Multiply. -1 times 2 is -2. Add. I get -7. All right, next thing is we need to assign the appropriate degree for this variable. We started with x cubed. We're dividing by x. What's my starting degree going to be now? X squared always drops by 1. Okay, so x squared, which means the next term is x, which means you have the constant, and then the last is going to be your remainder. Okay. Don't forget, you still have to do the calculus for this problem. And this should be easy because the first few terms will be power rule and the last term will just be natural log. Now, do I do a plus C for this problem? No, why not? I got bounds, right? So do 1 and 3. Upper bound gets plugged in, followed by lower bound, but no need to clean up. I should need to see that your numbers are plugged in. You can leave all this one big mess. Just protect the what follows after the minus sign with a big parentheses, but you don't do anything more than that. Number 9 is a little bit tricky here to get started. Where can I put that 3 from that natural log of x cubed? In front, right? So that's a little bit tricky here, bringing that 3 down in front. So I would probably start you off at this stage, since that it's hard to see that what to do with that 3. So imagine this is the starting point of your problem. 5 over 6x natural log of x dx. This one is a u substitution problem. Your u value being natural log of x, because we need something left over to pair up with this x with a derivative. So if my u value is natural log of x, my derivative is 1 over x, cross multiply, x du. That's perfect. The x's will cancel out. There's a 5/6 in front, and I'm just left with 5/6 natural log, sorry, 5/6 integral of 1 over u du, and then natural log as the antiderivative, and then bring back your x. I got a problem up here on the board. You guys want to try this one? So I see the three below. I can split it up into fractions. And it's really just two separate problems. Right. If I can split it into two separate problems, I don't have to do separate integrals, but it's a lot easier to see what's happening here, right? U substitution, e to the u, and this is just what? Just power rule, right?
I'm about to see that.
Wait, actually.